So now let's talk about the off-bow principle and the periodic table. This is how do you fill up that periodic table? So how do you stick the electrons in a given spot? So we're going to use something called orbital diagrams, and it represents the number of electrons an atom has in each of its occupied orbitals. So for example, the orbital diagram for oxygen is going to have a 1s, so we've got 1, 2, oxygen's going to come in with 1, 2, 3, 4, 5, 6, 7, 8 electrons, because n equals 8. Oxygen has 8 protons, it should have 8 electrons. We're going to represent as a little box each orbital that we've got available to us. So we've got a 1s, which will hold 2 electrons, and then we've got a 2s, that'll hold 2 electrons, and then we've got 3 p orbitals, each of which holds 2 electrons. So we've got this orbital box diagram here, and if you want to save time, rather than writing this guy out as a box, you can write it out in words. And so this 1s has 2 electrons in it, so we write it as a 1s2 to indicate 2 electrons. And there are 2 electrons in the 2s, so we call it 2s2. And here in the p's, we've got 1, 2, 3, 4 p's, so we're going to do 2p4. Protons are added one by one to the nucleus to build up elements. And electrons are similarly added to hydrogen-like orbitals one at a time to fill up your electron orbitals. So example, oxygen atom has an electron arrangement of 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, and 4 electrons in the 2p. Now, if you remember, we've got definitions of the ground state. That's our electrons in the lowest energy state. So most of the things we're going to be doing are looking at things in the ground state. Sometimes we'll look at stuff in the excited state. So that's when an electron is in a higher energy orbital. So you can imagine taking one of these guys from here and moving it up into a p. That would be an excited orbital. Right. Electron configuration is how electrons are distributed in the various atomic orbitals, and degenerate orbitals are orbitals that have the same energy level. For example, all 3p orbitals in a given subshell are what we call degenerate. So these guys here, 1, 2, 3, all have the same amount of energy. Electrons like to occupy the lowest energy levels possible in an atom, in other words, the ground state. You're going to fill in from lowest to highest energy in this pattern. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d5, 4d10, 5p6. Right? When I was a wee lad, the only thing you could do is just memorize this. Right? I will show you some rules to make this that you do not have to memorize this. Right? If we do things using our set of rules, we will arrive at this without having to have this memorized. If you want to memorize it, good on you, but I'm not making you do it. All right? So when we start filling these things up, a couple of things we need to keep in mind. First is the Pauli exclusion principle, which says that no 2 electrons in an atom can have the same 4 quantum numbers, and you have no more than 2 electrons per orbital. Right? And this brings us to the off-bow principle, or upbuilding, it's in German principle, which is electrons fill according to the orbital energies, from lowest energy to highest energy, right? Electrons are lazy. They want to be in the lowest energy they can, right? But if you run into the Pauli exclusion principle, right? So if you want to move into a neighborhood, you can't move into a house that's already got somebody living in it. Some of these energy levels are determined by something that's called electron shielding. Is going to change some of these energy levels a little bit, where you've got outer electrons that are actually going to be repelled from some inner electrons. So these outer electrons, they're going to see that nucleus, right? It's got a plus charge, but these inner shell electrons that got there first are going to repel them. Right? So they're going to feel on the outside a little bit less pull from this nucleus than these guys on the inside. So we call that Z effective, which is our effective nuclear charge, which is going to be equal to our actual nuclear charge minus any electron shielding that happens. Okay. So the Pauli effect. So there's Wolfgang Pauli speaking of our Pauli exclusion principle. So the Pauli effect was named after his bizarre ability to break experimental equipment simply by being in the same room as it. Pauli himself was aware of its reputation and delighted whenever the Pauli effect manifested. He was friends with the psychologist Carl Jung, with whom he shared a series of lengthy conversations Rules for writing our electron configurations. Electrons reside in orbitals of the lowest possible energy. You can only have 2 electrons per orbital. Electrons do not pair in degenerate orbitals if an empty orbital is available. So in other words, if you're moving in and you got a choice between an apartment that is the same cost with a roommate or an apartment with the same cost without a roommate, you pick the one and live solo. Orbitals fill in order on the previous slide, or an easy way to remember, follow this. This is called the diagonal rule. Back when I was at Wee Lab, there was no diagonal rule. So, you're going to fill up 1s, then you're going to fill up 2s, and then 2p, then 3s, then 3p, then 4s, then 3d, 4p, 5s, 4d, 5p, 6s. So this little diagonal rule, 1, 2, 3, 4, 5 s's, and then 2, 3, 4, 5, 6 p's, and then 3, 4, 5, 6 d's, and then the f's. So this little diagonal rule is an easier way for you to do it than that. Just memorize that, at least it was for me. So let's look at some of these electron configurations. So here's an orbital diagram for lithium. Lithium is going to have 3 electrons, right? We're going to put them into the 1s orbital first, and then our leftover one goes into the 2s orbital. If we go to boron, right? Boron is going to have 5 electrons. We'll fill it in 1, 2, 3, 4, and then the 5th one. So our off-bound principle says that you're going to add electrons one after another in the order that we just saw in the diagonal rule. In other words, from lowest to highest energy. Our Pauli exclusion principle says no more than 2 electrons in an orbital, right? So each of these little houses can only have 1 electron. When 2 electrons occupy an orbital, one is spin up and one is spin down. Right? And just by convention, we put the spin up ones in first, right? So here we've got carbon, which is going to have a total of 6 electrons. So we'll put 1, 2, 3, 4, and then we'll do spin up, right? Our next one would go spin up over here. Okay? So caution. If more than 1 orbital is available in a subshell, add electrons with parallel spins to different orbitals in that subshell. So no roommates, and they all go the same direction. Right? So if we go from carbon over to nitrogen, right, we added 1 more, it's going to go spin up. And then when we get to oxygen, we add 1 more electron. It's got 8 electrons. We'll go 1, 2, 3, 4. So 1, 2, 3, 4, 5, 6, 7, and then 8 comes in as a spin down. Now, it doesn't really matter where you put this because they're degenerate. By convention, you kind of do it left to right. Okay? So here's a table showing the orbital diagrams and then the full electron configuration if you wrote it out with words for the next bunch of elements. We also have something called the condensed electron or noble gas configuration, because if you look at this, right, it gets really tiring writing 1s2, 2s2, 2p6, right? 1s2, 2s2, 2p6 over and over again. And that's the electron configuration for neon. So you just pick a noble gas and say, okay, I'm going to put that in square brackets to say, yeah, it's like neon, and then we added some extra electrons on it. Okay. Right, so here's up to 19, from 19 to 28. There are a couple of weird spots on here. So like if you look at chromium, right, something weird is happening with chromium. Right? These are all, we got 1, it's a half filled, and then you're filling stuff up, and then why did my electron go from here? And we'll talk about that in a second. It's really because it's more stable, right? So this is a weird exception over here with chromium. And then if you get to copper, right, here's another one of these weird exceptions. Not all elements follow the order of the diagonal rule. Some notable exceptions are copper and chromium. So in copper and chromium, you're expecting there to be 2 electrons in that 4s orbital. And the reason why we don't see that is that you're taking one of these 4s orbitals and you're going to promote them, and you're going to put them into the d orbital, which is a little bit more energy. That's because that filled or half-filled orbital is going to be a slightly greater stability to it. Right, so chromium has 24 electrons. You're expecting this configuration with a 4s, 2, 3d, 4. Right? What you actually see is a 4s1, 3d, 5. That's what you absorb. And that's because half-filled 4s and 3Ds is more stable than the electron configuration that's expected. Same sort of thing is going to happen as above. With copper, so we get 29 electrons, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Right? So you're going to make a full 10 electron d orbital by taking this and giving you a half-filled s and a fully filled d. So copper is going to be 2 half-fills. This guy's going to be a full d and a half s. So that's what you're expecting. What you see is a 4s1, 3d10. Other exceptions can be found in the periodic table in the front of your book. But basically, they're going to be in that same column as copper and chromium. Like I said, there's a shorthand way to do this. You can use the noble gas configuration. You can represent all of the elements except for hydrogen and helium. So, for example, if you're looking at element number 15, it's going to have a configuration 1s2, 2s2, 2p6, 3s2, 3p3, right? But this 1s2, 2s2, 2p6 is the elemental configuration for neon. So rather than write all this out, you just plunk neon in there. So you can only use the next nearest lowest noble gas. You can't go and say the electron configuration for neon is neon, right? Got to write it out for neon. Or you could, you can't go to a higher noble gas, and you don't want to go 2 noble gases down. That'd just be silly. So, for example, we've got chromium. We've got 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. You got 18 electrons. That's the same as argon. So you can rewrite that as argon 4s1, 3d5. A noble gas has to go in the brackets. You can't pick another element. All right, so you can't do like, whatever element 17 is, and then just change that last bit. It's got to be a noble gas. Okay, so valence electrons. They're the ones that are on the outermost principal quantum level of an atom. So these valence electrons are the ones that are going to be doing most of the interacting with other atoms, and so they're the ones that are kind of the business end, right? They're in the up-and-coming neighborhood. They're the ones who are, ripping out the linoleum and putting in hardwood floors. They're the ones who are doing all the stuff. For example, for a sodium atom, the valence electron is the one in that 3s orbital. The inner electrons are termed core or inner shell electrons. They don't do too much. They're there. They're not going to move. Right? It's the ones on the outside, our valence electrons, or outermost electrons, that are going to be doing all the interesting stuff. The elements in the same group on the periodic table have the same valence electron configuration, and so therefore display similar chemical behavior. So if you look at all the guys in column 1 on your periodic table, they're all going to have a S1, one electron in an s orbital. All the guys in column number 2, your alkali earth metals, are all going to have 2 electrons in an s orbital for their valence electrons. Some of the groups in there, you've got these transition metals. Those are the ones whose configuration is obtained by adding electrons into the d orbitals, right? So that's that stuff in the middle. Those guys get a little wonky and a little bit tricky, right? So we saw with chromium and copper how, okay, maybe we're going to borrow that. When you're dealing with these elements and starting to make atoms and molecules, remember that that d is actually inside, physically speaking, inside the 4 S's, right? And so if you're going to do some chemistry is going to happen with this because it's physically outside this 3D. 3D is higher energy, but it's physically inside. After lanthanum, the lanthanide series occurs, which corresponds to the filling of the 7 4f orbitals, and the actinide series corresponds to the filling of the 7 5f orbitals. The main group and representative elements, so the labels for groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A indicate the total number of valence electrons. Remember this whole octet thing, 8 electrons, that main group is looking at S and P's. 2 plus 6 is 8. Each member of these groups has the same valence electron configuration. And so everything in 1A is going to be having these are all in our S block, right? And if you're in this column, you've only got 1 electron in your S block. And in this one, you've got 2 electrons. So this would be a having an outermost valence electron configuration of 3s2. And this guy would be 5s2. This guy would be 5s1 and 4s1. If you're looking over here in the p block, right, it's 2, 3, 4, 5, and 6p, right? So this would be something where it would be 2s2, 2p1, 2, 3. Over here, if I pick this element, it would be 5s2, 5p, 1, 2, 3, 4, 5. So you can use the periodic table itself to give you those electron configurations. All you're doing is working it backwards, because the reason why the periodic table is shaped the way it is because of those electron configurations. So you can use it to predict what your electron configurations are. Right? So given the electron configurations for sulfur and cadmium. So sulfur is element 16 and resides in period 3, where the 3p orbitals are being fulfilled. So since sulfur is the fourth among the 3p elements, it has 4p electrons, and its configuration would be 1s2, 2s2, 2p6, 3s2, 3p4, or neon 3s2, 3p4. Okay. Cadmium is element 48, and it's located at period 5 at the end of the 4d transition metals. It's the 10th element in the series, and thus has 10 electrons in the 4d orbital, in addition to the 2 electrons in the 5s orbital, which precedes it. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, or krypton 5s2, 4d10. We saw earlier that electrons can be taken away or added to an atom. When we do that, we're going to form ions, and we're going to write the electron configuration to represent that gain or loss. So sodium atom that's neutral has 11 electrons, and its configuration would be neon 3s1. Our sodium cation only has 10 electrons, and we'd write that as neon 3s0. Right? You're going to take electrons from the outside in. Think of it as last hired, first fired. Right? So cations, remember, they are positive. They're missing an electron. Right? Cations are positive. Our D-transition metals can be weird. So iron, for example, you've got this configuration where our outermost electrons are 4s2 and 3d10. That's our neutral one. We can form a +2 or a +3 ion. Right? And they're going to lose those electrons from the S before they lose it from the D. Right? So you're going to form our 2+ ion is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s0, 3d6, or argon 3d. If you're doing a +3 cation, you're going to take away from these two S's, these two electrons in the S orbital, and then you're going to take it away from that D orbital. An anion is an ion with a negative charge, so something like sulfur, which has 16 electrons in its neutral form, would have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. S2 minus gains 2 electrons, and this electron configuration becomes 1s2, 2s2, 2p6, 3s2, 3p6. So you've gone from 4 to 6. Okay. If you have the same number of electrons, so oxygen 2 minus, fluorine 1 minus, neon unchanged, sodium plus, and magnesium plus, right, they're all going to have 10 electrons. So it would be oxygen gaining 2, 8 plus 2, fluorine gaining 1, neon would be neutral, sodium would lose 1, and magnesium would lose 2. Now, these are called isoelectronic atoms. Iso meaning same, and electronic, electrons. Right? So they're all going to have the same electron configuration, 1s2, 2s2, 2p6. So if you've got 10 electrons, right, whether you're an ion, neutral, cation, you're going to have the same electron configuration. Okay? If you are an excited state, right, so if you've got a sodium, right, and it's neutral, it's got 11 electrons, and you have your neutral configuration, 1s2, 2s2, 2p6, 3s1, you can excite it from a P to an S, right? So you can take one of the guys out of here, put some energy into it, and move it into a 3s. Or it can be even more excited, right? So maybe you move it from a 2p orbital out into a 5d. So our periodic table is made based on the order of electron filling. And so what similarities you find within the families on the periodic table are all kind of due to those valence electrons, right? So give them a home where the electrons don't roam. Right? So our key points that we've covered so far were our magnetic spectrum, our wavelength frequency energy intercalculation, the idea that light can exist as a particle and a wave, a photon. We talked about the photoelectric effect, which gave us the idea of that a photon can act like a particle. We talked about emission spectra and how that led to the quantized energy levels on individual atoms. We talked about ground state versus excited state. We talked about the Heisenberg uncertainty principle and how that relates to knowing where an electron is. We talked about our different quantum numbers, N, L, M sub L, M sub S, that are used to predict possible sets. So those came out of the Schrödinger wave equations, which came from the idea that we needed to reconcile that Bohr model. We've talked about electron configuration, so how to identify and write an electron configuration and our noble gas configuration. We talked about the rules like Pauli exclusion principle, Hund's rule, and the Aufbau principle that told us how are we going to fill up those electrons for atoms. And we talked about neutral atoms, we talked about isoelectronic atoms, we talked about ions, and we talked about excited atoms. So now I'm going to talk about some commonly observed periodic